So up to the yesterday's talk, was it distributed already, or not still on your hand that the PDL file?
No. It's not distributed. I put it on the homepage.
Everyone has access to it.
So you have it. Okay, good. So my talk tend to be sloppy, so the precise statement is on the written notes. So they apply Abson's applied. Of course, purpose is not to study abstract Banach space. It is on phonemic algebra G abelian alpha action, and M alpha E meant to be X in M such that this alpha spectrum of X is sitting in E. The E is closed, subset of the G hat dual group. And it has a property, then very natural property. M alpha, maybe I write there. Spectrum alpha of X, Y, X and Y in M is contained in spectrum alpha of X plus spectrum alpha of Y, and unless one is compact, the set of sum is not necessarily closed, so you close it. And okay, that's the statement one. And they say it's very natural that E times M alpha F is contained in M alpha E plus F. Once again, you must close it. And let me see, the second one is, spectrum, alpha spectrum X star is minus of a spectrum of alpha of X. And the prime is M alpha of E, adjoint is M alpha of minus E. Okay, that is. Okay, now what happened is this M alpha E is the set of those elements whose oscillation modes are in E. Okay, so then obviously fixed point M alpha. Okay, this is for in this reason the spectrum, alpha spectrum is 0, that doesn't move, so no oscillation whatsoever. And M alpha acts on the both sides to the M alpha E with the two-sided module from the left, M alpha from the left, the M alpha, because of this spectrum in doesn't, if X, one of them is the fixed point, this is 0, nothing happens, so the same. So now with this in mind, okay, the P alpha of E is the supremum of all left support of X. I explained in a minute what left support means, and the Q alpha of E is also then this right support of X, X in M alpha of E. Okay, when you have operator for x, then you have polar decomposition, or u, for that matter, x star x square root. Okay, the left support is you take the range projection, the x Hilbert h closure is the left support of x of h. Okay, you can obtain this one if you like. Is a strong star limit, sigma strong limit of x star, this range xx star to the 1 over n. Okay, that's n infinity. For that reason, also then that the domain part, orthogonal complement of the null space, orthogonal complement of the zero space is the right support. Another word, which is the closure of the range of the adjoint. So that SR of X Hilbert space projection is the X star H, its closure. Okay, and for the same way, this can be written as strong limit of x star x to the 1 over n. Okay, then you get the right projection. Okay. Okay, then what happened is, what happened is that first alpha, automorphism alpha, spectrum alpha of x equal to spectrum alpha of alpha s of x. Because G is commutative. The shifting the given element by group element does not change mode. The oscillation mode unchanged. So alpha invariant. Now you think of what this. This one was taken, of course, this is a projection in M. This is a projection in M. And this, and alpha, it took all of them, so this is invariant under alpha. Invariant under alpha. So this belongs to the fixed point. One thing is in the fixed point. Next is that if you have unitary in the of the fixed point, ux u star of alpha s is not, this being fixed today, this morning already quite a bit handle this phenomenon, u goes outside. So u does not move u of m alpha e u star equal to m alpha e stays invariant under the inner homomorphism given by u. That means that if you rotate p alpha u e by the unitary in the fixed point, okay, u doesn't move, and this just goes to the inside, right? U SL of x u star is general fact SL of ux u star. The support also moves accordingly. So, and so you are taking all of them. So this does not move by inner automorphism. U of PR half E, U star equal to PR half E for all U in the unitary of the fixed point. Consequently, PR half E belongs to the center of M alpha. I write it as C alpha. So this projection belongs to the center of the fixed point algebra. And the same is true for Q alpha V. It's also the projection in the center of fixed point. Okay. If we have something like excuse me, this M alpha to be to the top. Yes. M alpha fixed point happen to be factor, for instance. Then no center, that means this is equal to 1. All the way is equal to 1. Okay. And with this, what Abson did is the theorem of, okay, this is not directly related to our objective, but since we talked appreciating the Abson's work, maybe I should also present at least what he aimed at in his paper. This is the theorem of, or maybe Borges was the first, Abson. The given one parameter automorphism on the phenomenology M, then the following condition is the equivalent. First is there exists one parameter unitary group such that alpha sub t is odd ut t in R. Unitary group means T from R to U of T, U of M, strongly continuous, and the U of S plus T equal to US UT, S and T and mu. And which admit the following spectral decomposition, okay, from 0 to plus infinity, not minus e to the I lambda t d. Well, I tend to write it in lambda. Spectral projection of one parameter. Namely, spectrum U is positively supported. The positive, only positive mode. Second is Q alpha of lambda plus infinity infimum for lambda positive equal to 0. Yes, I wrote, okay. So Those two statements are equivalent. And another was this alpha, the one-parameter automorphism with the oscillation mode is somewhere it's shrinking down. Then you have this type of expression of one-parameter automorphism. Okay, so that, and the proof is constructive because this E lambda spectral projection is concretely given by infimum of Q alpha of T plus infinity T larger than lambda. So this even if you know this condition, then you can explicitly written down the spectral projection for a spectral measure of one parameter intergroup, just looking at this gadget, global object, of course. Yeah. And it is then, well, with some, not much involved, but still no need to do something. But it is also if you expect energy operator to be positive, then the suppose you have U of t to be 0 to infinity e to the I lambda t dE lambda, and the U of t normalizes so that ut gives rise to one parameter automorphism M, okay, without knowing U of t being in M or not. Then Hobson's theorem tells you this is in automorphism. It does not say ut is containing M, but there is another one parameter unitary group inside M which implements that automorphism. Of course, if you hit by this, then this goes to the commutant. Okay, if ut star ut belongs to the commutant, and that gives you the splitting of ut between M and its commutant. Okay. So this is the triumph for Bill Hobson. He was a bit satisfied, happy, and he came down to UCLA to present his work. And it was, well, much better organized than mine. And so I was very moved by his work. It was in the spring of '72, as I told you, that very early in April. Okay. Well, first of all, the Hobson was a former student of Henry Dye at UCLA. So UCLA was his homeland, in a way. So he came down to UCLA, Los Angeles, and proudly he showed, I have now the constructive proof of Borges' important theorem. And the Borges theorem, well, I'll state, since we have come to this far, maybe I'll spend a couple of words that what's the status. Before Hobson, Borges' theorem was proven based upon the following theorem of Sakai and Cadison. Okay, first of all, A, C-star algebra, and the linear map from A to A satisfying following Leibniz rule. Okay, Leibniz rule does not require algebra to be commutative. Okay, so this is, it's called derivation. Well, derivation was first studied by, Kaplansky. Well, I learned through Dick Carlson that Kaplansky raised a question about derivation on C-star algebra. And easy thing, well, those are Chicago group, okay. In Chicago, the easy thing very quickly showed that there's no derivation on commutative C-star algebras. And at any rate, that being algebraized, Kaplansky went on for the derivation, theory of derivation, and the left open question that, okay, remember, isomorphism between C-star algebra is necessarily not isometry, but homeomorphic, that is non-bounded both ways by continuous in norm, okay, or the isomorphism. That is a known fact. And he raised the question, is, okay, that relates to the Hilbert fifth problem. How much algebraic structure of object controls the topological behavior? And the question raised by Kaplansky is one of those. The derivation is reflecting the multiplicative structure of algebra together with addition. Okay. And is derivation bounded? Okay. And Sakai proved the following. Okay, it's every derivation on a C-star algebra is bounded. That this is Sakai. That means that the write immediately exponential t delta to the n in the runs from 0 to infinity is one bounded norm continuous. Is norm continuous one parameter group of automorphism. Okay, of course, if you don't assume anything about delta, you don't expect this one parameter automorphic group is indeed star automorphism, not necessarily star. Indeed, every derivation, okay, delta star of x, if you define to be delta x star to the star, then if you have delta is delta plus I delta minus delta star to I, and if you look at this one, then this one is, say this is delta r of x star equals to delta r of x. So those are the star derivation. And the if derivation is a star derivation, then this is one parameter group of star automorphisms. Okay, that much is easy to, yes?
Why is it an automorphism, this, if you do something like this?
And this one?
Yeah.
Okay, this is you believe this is Taylor expansion. And this derivation property tells you that the multiplicative. Yeah, that's
Automorphism.
It's yeah, it preserved okay. E to the t delta times e to the minus t delta equal to identity. That is very quickly you realize. At the same time, this equation tells you this is all the multiplicative. How to do that? You don't need to work on all the expansion. What you need is just differentiate this one. Then delta pops out. And in Cauchy initial data, uniqueness of Cauchy initial data problem tells you that that mapping is multiplicative. Okay, so of course you can do the hard work expanding everything, and then because showing multiplication is really expected, but it's a hard way to go. It's better to appeal to the uniqueness of the initial value problem or solution. Okay, what else at hand for Borges or the Sakai-Cadison theorem? Both papers appears on the same issue of the analysis. It's not the joint paper, it's independent. That's every derivation for Neumann algebra. With inner, what that mean? I.e. delta of x equal to ax, which means x to xa for some a in M. Okay, this is a beautiful theorem, a triumph of the early 60s in operator algebra. However, people criticize, of course, non-specialists. Well, the derivation is bounded affair. In application, where is the bounded derivation? Almost none. Whenever you write a differential equation, it's unbounded most of the time. Differentiation is a hard object for analysts. And so it was criticized the bounded one, forget it. But Borges didn't forget. He was very impressed by the deep theorem, and he proved the theorem is very needed for the mathematical physicists, that the energy is expected to be has a positive spectrum, right? Is that they don't want to consider negative energy to the minus infinity, bounded from one point on, usually from 0 on. And then if you have one parameter unitary time evolution, which normalizes your phenomenal algebra, then that has to be inner. So that means if your algebra is observable, then that means energy is the limit of observables. That is philosophically quite a triumph for the theoretical or mathematical physicists. Okay, so that's a deep theorem had immediate application in mathematical physics. Okay. I'm lucky not criticizing. I'm not among those who did not appreciate the Sakai's theorem. I was quite positively impressed by their achievement. Now, okay, that much is about derivation. Well, if we are about to leave the absolute theory, but if you think about the Banach algebra of of A is generated by Banach algebra. Alpha F in L1 over G, and then take maybe closure in the bounded, in the abstract sense then. Then this is also commutative Banach algebra. And this, being commutative Banach algebra, you have actually Banach algebra spectrum, Gelfand spectrum, is indeed spectrum of alpha in G hat. So it is very natural. All right, so let's move on. Let's see, I got this. No. I got, Okay. Now I move on to the Kohn spectrum. Okay, we have had Kohn derivative this early morning, and now he had at the same time. Well, he was the Alan was equally impressed by Abson's achievement, and he thought that okay, so now we discussed this. He added one chapter to the spectral analysis of abelian group action of Neumann algebra. So the situation is the following: M group G in the alpha and the abelian. Those who are not familiar with Pontryagin-Duality just restrict to the real line. That's good enough for the purpose. Now, what he had, M alpha, then you can have projection. Then you have projection, ME of that M, that's corner, that's a reduced algebra by projection E. Acts on EH. Acts on EH, okay? M sub E, the other set, this is the ME, but it represents only EH. Now, alpha S of E equal to E, so EXE alpha S equal to E alpha S of XE, which belongs to ME. So M reduced von Neumann algebra is globally invariant under alpha. So call it to be reduced system. So ME group is the same. Now we write it alpha. That's a reduced system. Reduced by projection in the fixed point algebra, M alpha. Okay, then what happened? Oh, okay. Now, what Kohn did around it is gamma of alpha is intersection of all the spectrum of reduced one. Is in the projection of M alpha. Of course, you don't take the zero projection. If you take zero, then everything will evaporate. So you take non-zero projection And okay, I present the result in a bundle. Okay, some part is around himself, some part is together, so on and so forth. But now first is one. Okay. This is called the Kohn spectrum or essential spectrum. Kohn spectrum alpha. Okay. So when you have alpha, you have an Abson spectrum, and intersection of all Abson spectrum of reduced action is Kohn spectrum. Okay. What happened is gamma alpha equal to gamma of alpha u for all u co-cycle perturbation does not change the Kohn spectrum. Okay, so that the co-cycle perturbation invariant. You think right away, wow, that means the modular automorphism gamma spectrum is invariant. Does not depend on the choice of weight or state. That's the statement is there, right? Number two, let me see. Oh, yes. Gamma bar alpha is a closed subgroup of G hat. Okay, Abson spectrum need not to be a group. Okay, look at the positive spectrum, then it's not a subgroup. But the gamma spectrum is a closed subgroup. For real line, how many closed subgroup? You know everybody, all the subgroup is your friend. It's a zero, the trivial one, or fixed number times integers, or whole real line. Okay, that's immediately consequence from this theorem, right? Number three, gamma alpha plus spectrum of alpha is spectrum of alpha unchanged. So spectrum, the gamma of alpha is small enough, so it does not alter this. This is leave it invariant. Number four, gamma of alpha equal to the kernel of the dual action restricted to the center of cross product. Okay, this is the where this Kohn Takesaki joint work. The fourth statement is joint work, and the 1, 2, 3 work around himself. This is CT. Okay, the proof is natural. Well, this deep theorem proof requires, of course, a bit of work. It's not that comes so cheaply. Now, so the corollary is the following. If M is a factor, Let me see. Let me make sure I'm not derailing from what I planned. Oh yes, I think here's go. So it's a factor. Then gamma of sigma phi is a closed subgroup of modular Liouville. Yes?
What is the last statement in it?
What?
The last four.
The fourth statement is gamma of alpha. So the corner spectrum alpha is a kernel of the action of the dual group restricted to the center of the cross product. Okay.
The dual group is a semi-group. It's a group. I mean, what is the meaning of kernel of the group? It means intersection of the all every T.
There is a homomorphism from this into the.
No, for every T of the.
Not every T.
No.
Alpha has the group which gives the trivial automorphism on the center. Yeah.
So technically, why we need the Alam did not state this one is that he was okay. The center of the cross product is L infinity of x mu, standard measure space, and alpha t, the dual is acting on the measurable, not Prism way, but quasi-invariant measure, and almost everywhere real line is continuous. So null set is fine, but if you move that null set along the orbit, then it's no longer zero measure. So what we needed to prove is to replace this by C-star dynamical system, C-star algebraic covariant system, which is dense inside. Then you can have a topological methods available, compact set, etc. Those are available. But if you stay working on L infinity, then almost everywhere a question bites you. But at any rate, is that only the three possibilities? Kernel is 0. Yes, and then Tg, T of course positive, and we take lambda to be e to the minus. I think this 2 pi is always okay. Instead of writing it, I write this way. Minus rho lambda z. Okay, so this is t. So okay. This time, this is type 3-1. Okay. This is type 3 lambda. This is of type 3-0. That's the new classification, subdivision of type 3 factors into those of type 3-1, type 3 lambda, type 3-0. Now, remember, in the factor case, alpha hat on the center of centralizer has to be ergodic, right? Otherwise, if there's any fixed point, Then second cross product, which is the original one times type 1 factor, that the fixed point survive commuting with everybody. So it's not a factor. So factor case, alpha hat action on the center of the cross product has to be ergodic. Ergodic, at the same time, kernel is everything. What that means, action on the center is ergodic, yet nobody acts. Your object has to be one dimension then. Means that this M cross sigma phi of R, which we write M tilde, is a factor. Has to be factor, right? Now, next one. If this is 3 lambda, it's periodic. Okay, periodic. So one parameter periodic, one parameter autonomous system. So sigma alpha hat, which I had theta sub t restricted to the center of M. Oh, well, why don't we write it M tilde? Sigma M tilde is identity. Okay? And yet, it has to be ergodic. That means a compact abelian group acting on the periodically, and ergodic means it's transitive. So that means in this case, center C of M tilde R theta, it has to be conjugate to the L infinity of R divided by minus long lambda Z, and theta acts on the translation. So that's become very visible. How it now. This one is now real lines action on the center is now nobody is trivial, so moving everybody. Okay, then the case is ergodic at the same time if M is a factor. Then one possibility is transitive. So in the case of CR theta is L infinity of R acting R by rotation, translation. Okay, that's the transitive. Then you can see very quickly, well, okay, center, real line, translating, M tilde sitting on top. Then when you make a cross product, then that means this disappear. And on top is still sitting there. So in that case, if this is the case, if and only if original M is semi-finite. It does a trace. So trace on M tilde survive through this translation, the cross product, because that it's on just a real line. Indeed, you can make a perturbation so that action become translation on the real line, nothing on the fiber, on the M portion. Then that's if you make cross product like that, then you have M original one times elevate, so that's semi-finite. Otherwise, so that case, okay, this is a bit shortcoming. So except those, then thanks to real lines commutative, this becomes properly ergodic. Properly ergodic. Okay, properly. So the no single orbit carries all measure. So, ergodic. So this implies C R theta is properly ergodic. So this is the case you call 3-0, not that this one. Okay, this was semi-finite, so nothing happening. That is, then you can see right away the modular automorphism ought to be in now. So those are the classification of type 3 factors into those. It was done in his thesis. Okay. Now, one more comment about this 3 lambda case. Let me make sure I'm not derailing when you talk. Oh, okay. Yes, maybe I'm, well, this is derailing from what I prepared, but I can't stop telling you. Okay, it's a periodic case with period minus long lambda, so period t. And all fiber sitting over, right? That's the M tilde. M tilde looks like that. The cross-section algebra real line and one parameter automorphism is at the base on the center it's circulating. Okay, what happened? At the same time, trace is being scaled down. And if that means when you have weight to the up to period t, t is minus long lambda. Wait for the precise period t, then this theta t does not act on the center, that's a count, right? So it theta t acts on each fiber m tilde of, say, omega. How much change the trace? E to the minus t, which is lambda. So what you discover if you look at just m omega, you say not the m tilde 0, that this is a factor, right? That's the factor. Trace is scaled down by lambda. So, and now theta t, this is, now it is not a continuous but a discrete, the integer acting on each. So that the integer, but by theta t. So you obtained factor n, of course type 1 factor, no automorphism scale trace down, so you see immediately this n has to be type 2 infinity. Okay, type 2 infinity, and the automorphism, single automorphism this time, theta t, scales trace down by lambda. And if you make under the theta t, the integer, that cross product, then this is isomorphic to m. 3 lambda factor has a discrete decomposition because of this. And this is so-called cone discrete decomposition of factor of 3 lambda. Okay, so 3 lambda has that. Now 3, 1, okay, n is a factor, so nothing you can do. It's very nice that you have said one parameter order one system scaling trace down, and you make cross product, you end up with 3, 1 factor. Okay. Now I want to return to the original plan. This much is a bit of the side step from my plan. But when I start talking about that corollary, then I couldn't stop myself of talking to this. Okay. Now, yes?
So type 3-1 factor can never be seen as
I'm sorry, say again?
So if for a type 3-1 factor can never be seen as a cross product with respect to a discrete group?
That can happen. That can happen. How it occurs. For example, suppose you have m tilde to infinity factor, so and scaling like that, yeah. Then you make rational number, make cross product based on rational number, not a real number. You end up with 3, 1 factor, and it is actually discrete decomposition. But this is not. So when you do that further, and then you analyze what the continuous decomposition is, a bit more complicated to say it, but it is still 3, 1 factor. So there is a discrete decomposition of 3, 1 factor possible. Okay, no, but not always. However, that is the example which Alan cooked up afterwards. There. But discrete decomposition, then group become a bit more complicated. Well, of course, you cannot do it by a single automorphism. Oh, well, I wouldn't say that. In that case, the so-called group measure space construction, that is discrete decomposition, definitely, but it's not directly linked to the modular theory. So it's not such a decomposition is by no means unique, for example. There are many different wave writing. Okay. Now I want to give a meat to the whole theory, something to eat. So, this morning we talked about 2x2 matrices over von Neumann algebra. Now I want to talk about the 2x2 matrices over scalar. Okay, so that is very nice to see it. So, Mn is more to C. And fix lambda between 0 and 1. And okay, the element, general element looks like here. However, unlike this morning case, those xij are scalars. And I define Mn because it's lambda involved. We take this lambda, square root of lambda, square, maybe lambda 1/2 plus lambda minus 1/2 plus maybe here is so 1/2 lambda minus 1/2 and lambda 1/2 plus lambda minus 1/2. Okay. And here x11, x22. Okay, that's the state. Okay, if you just assume 1, then this sums up to 1. So omega n is a state. So mn omega n lambda. Now, you consider following formal expression. 1 afterwards. Okay. And make the linear combination of those, allowing distributive law among those products, such as, for instance, lambda alpha x1 cross from beta x2 y1. The rest is the same, x2 equal to alpha x1 plus beta y1 tensoring x2 x3 like so. Okay, but you take identity from certain point on. Okay, so they make a linear combination of those, and then become naturally that become star algebra. So that's the infinite algebraic tensor product of n. And it had natural star operation. And since matrices algebra is the unique, it has a unique tensor product norm. So it's actually M2. M2 to this 4, M to the 2 to the n, like that. So you take inductive limit, for instance, and then you can make a completion. So this is C-star algebraic tensor product of Mn. Call it M. Okay, and so the element there is not end at a certain point just by 1, but the all element there is that the tail portion is approximately identity, almost identity, always. Okay. The tail is near the 1. Okay. Then the C-star algebra is this, and it is actually, it has a name, U to the n type of UHF algebra of Grimm. But and you extend omega lambda is the tensor product of omega n lambda. Okay, thanks to this, those are the end at the finite set portion. So the product of this one converges because from certain point on, it's multiplying just 1. So this product makes sense. And it gives you state on this C-star algebra. So you have omega lambda. So that means pi lambda of m xi omega lambda. Well, Hilbert space H lambda by GNS construction omega lambda. Okay, and then make a weak closure. You end up with von Neumann algebra indexed by lambda. Okay, that's we don't know what the omega R lambda look like at this point. This was already studied by de John von Neumann in the paper appeared in the Brazilian journal. And also studied by Pukansky. Pukansky proved this R lambda as a property L lambda here, etc. It's near closely related to the Marie von Neumann's property gamma. But in any case, drama didn't come from them, but comes from the Bob Powers in the 67. Now, you look at the following. Okay, look, fix n and m1 tensor mn. Okay, from this term, I don't care. And the sigma is a permutation of 1 through n. Okay? And I consider the sigma to be union of those sigma 1 n. So, in other words, S stands for the finite permutation of a natural number. Okay, you exchange the finitely many of them and leave the rest unchanged. So, take sigma and you xn and then identity on and this one and x sigma 1 x sigma n, then identity on. Okay. Those permutation of the components, this step gives you immediately that automorphism of first algebraic tensor product. And, okay, it's of course the metric given by the C-star algebra structure. It's isometry. It has become an automorphism here, and thanks to the way we constructed omega n lambda, omega n has every place the same states, right? We planted the same thing over and over again. And the sigma is just changing. Nothing happens.
So it's preserved by the state.
So omega lambda is invariant. And that means it goes over to the weak closure. So sigma becomes automorphism of R lambda. At the same time, what is this? In this case, what the sigma does is the sigma belongs to the automorphism of M1 tensor to the Mn, which is M over 2 to the Nc, or the automorphism. First n component, that's 2 to the n by 2 to the n matrix. Every automorphism is inner there. So you do have U sigma in the M1 Mn, and then U sigma adjoint gives you sigma. Okay, U sigma is element here. The unitary, of course. Unitary of okay, you can view this as unitary of C-star algebra. Then what happened is, as I told you, U sigma, the sigma itself does not move state. So omega lambda at U sigma is omega lambda circle sigma omega lambda. So U sigma does not change this omega lambda unchanged. what this morning Sherman told us, such a unitary belongs to the centralizer of omega n, right? So this U sigma is in the R of omega lambda, centralizer of the state omega lambda. Because it's odd U sigma does not move the state. Now, at the same time, if you take, say, sigma n is the change between 1 and n to the 2 to the n plus 1, 2 to the n plus n. Just change it. That's easy to guess, right? Now, what happened is sigma n of x, y, omega lambda. Say, take x and y in the algebraic tensor product, not the completion. Then if n exceed where x lives, it's a finite place, or y as well. And the n, if you take n large enough, then the sigma and x moves far away from where y x. Then omega lambda is the product of that, right? So when n is large, this is omega lambda of x, omega lambda of y for n large for the algebraic element. If it is C-star algebraic element, you take limit. So it's a product. And that's true for everybody in the weak closure as well, which means that sigma of n of x moves to the omega lambda of x 1 sigma weakly. Okay, but such a thing is carried out by the inner automorphism U sigma n. It's U sigma n. In other words, if operator in R sub lambda commute with U sigma n, what's happened? It doesn't move. It's not the product then. It cannot be the product. So U sigma n, the fixed point of U, okay, it's not a group or anything like that. But what we know is if you take U sigma n over the prime to the R lambda, what is precisely we know the scalar. Nothing else can be stopped, but fixed. So that means that R omega lambda relative commutant in the R lambda is scalar. So the fixed point is very fat. Okay, so you know that then what is it? That means this is in particular factor. This the fixed point, the centralizer R lambda is a factor. So this is a factor. Then spectrum of sigma omega lambda, nothing cut down, right? The center of no projection of the centralizer. So this is gamma. What is it? Then we know that the modular automorphism of sigma n is given lambda t sub n is odd of lambda minus 1 minus I t over 2, 0, 0, this here, minus it over 2. That is the sigma, and it is tensor product of those. So and you have sigma lambda t equal to identity n tau for all uniformly on n. Uniformly identity when t hit the capital the period t, it is then that's identity. So this modular the morphism and the periodic at t. So what is the spectrum? Is the Tg, which is rho minus lambda z. So this is a factor of 3 lambda. If you change lambda to mu, you have r lambda and r mu, because the gamma 3 lambda and 3 mu never be isomorphic when lambda and mu is distinct. So this is the theorem of powers. Robert of the 67. So you have had already continuously many factors of type 3, 1. Oh, excuse, type 3, lambda. The lambda moves from 0, between 0 and 1. Yes?
So did Powers
Yeah.
know the 3 lambda this thing, or was it after Kohn?
No. The 67 Kohn was traveling somewhere in Cambodia. So he was not operator algebraist yet, 67. He was still maybe in the undergrad student. So, so that the gamma affair comes afterwards. That's 67.
303 lambda and 31, that was only done by Kohn.
In the published paper, it was 73, and Kohn himself came to gamma in the fall of 72. So there's a 5 years gap. Yeah. But nevertheless, that's 67. It was sensation. Because at that time, I'll tell you, how many factors are known? Guess.
9.
We had, for the 2-1 world, you had only the approximate finite 2-1 factor, and the free group one, that Marianne von Neumann, that 43, and the early 60, Jack Schwartz added another 2-1 factor, and like that, the 3 in 2-1, and another 3 in type 3.
There were something by Lance and Dixmier, so there were 9
Yeah.
at one moment.
In any case, it's 3 or 4 or 5th one, 7th one, etc. like that. So if you look at the progress of that recognition of different factors, you can see the impact of this type 3 achievement of both powers. There's no way to break it down by the Kohn. Historically, that's very important. Maybe since we started to talk about the history, maybe how it goes, so how it went. This was the powers in the 67 spring reported at the Baton Rouge conference. And unlike Tomita's work or Hugenho's, Hugenho's winning, this was highlight, and everybody was overwhelmed by that. And then Araki was the asymptotic ratio set and the row set, row set of M, distinguishing type 3 factors. That was around the published one is 69 ohm. Okay, and then 69 ohm. At the same time, at a different corner, that Krieger comes in the studying the group measure space construction, and turns out, well, Krieger was very much influenced by Araki Woods. And being ergodic theorist, he went a little bit further on. And he classified all 3-0 AFD factor. No, I would say 3-0 measure space constructed factor. He classified 3-0 constructed factors. And then that's around 74 or so, 74, 75. And then Kohn came along with Big Bang at 70, after my 74, 70. Actually, it was done in the spring of 75. All specialists knew his work. It's a preprint form. But although publication is spread from 75 through 78 or something, 3 years or so, did it this AFD all Krieger factor. 3-0 are all Krieger factor. That's what Kohn did. To reduce to the Alan did not work on the measure space. His work is on the reduce to the Krieger's work. And the Krieger's work took, although the history doesn't go that way. Okay, let's go back to what I planned. Oh, yeah. Now, I move on. Actually, the 3-1 factor is the motherland of all three type 3 factors, at least in the AFD factors are concerned. If you have a 3-1 factor, you can create all other factor out of that given 3-1 AFD factor. Okay, now let's construct 3-1 factor. Yes, for this.
How power-proof they are non-isomorphic? Type 3 lambda and type 3.
Actually, I mean.
How power-proof that type 3 lambda and type 3 mu are non-isomorphic?
How far?
Power-proof.
No, how Powers did the proof of that?
Oh, how he did it?
Yeah.
Non-isomorphic.
The modular theory is not available to him.
Yeah.
He had to do it with your bare hand.
By hand, yeah.
That shows his power. Yeah, nothing available to him. So it was so that's what his physical insight is something very, very impressive in that regard. He was Arthur Whiteman's student, and he did it for the thesis, for his thesis. And when he arrived at the University of Pennsylvania, the Sakai was so surprised that the Powers knew nothing about actually the phenomenological theory at that time. Simply, he did it, this one, by bare hand. You know, usually you respect, oh, such a great result, and he is a Superman or something. But the Powers wasn't, that he has a super powerful man. And he didn't need any theory to use, that he did it by bare hand. However, one thing is important, not commonly recognized by the operator algebraists is asymptotic commutativity, which is at that time the heart of mathematical physicists because of the Rudolf Haag's emphasis of the locality. When you have physical quantity separated space-like, then anything on the one does not interfere the others. So it is simultaneously measurable. That means the physical quantity there and that commute. So when in the region you shift to the infinity, then start commuting. So that asymptotic commutativity is in their heart. So he used that asymptotic commutativity very wisely. For instance, if you look at, yes, here's a, okay, when you move this along this n, then become a product state. Those are called cluster property. Well, ergodic theorist says it's the mixing, but mixing, the cluster property has more dynamic flavor behind it than the mixing property, and Bob used that asymptotic commutativity plus clustering property very, very clever way. And he proved this majestic theorem as of that time. Although this development measure, the modular theory consumed his result, but still his achievement is still shining, at least in my mind. But at any case, when you study the actually factor of phonemic algebra factor, then you have to run through this infinite tensor product matrices algebra, very concrete. Now we want to have a concrete construction of 3-1. Now instead of 2 by 2, I take now 3 by 3 matrix, and omega of x equal to, you take lambda mu positive, and lambda over mu is not rational. And x11, 1 plus lambda plus mu plus x2 mu lambda x2 2 1 plus lambda plus mu plus mu mu x3 3 1 plus lambda plus mu. Okay. Now you do the exactly same construction. So you have now 3 by 3 matrix tensor product, and omega, there's omega n. This is the tensor product of omega n. And then you construct the pi omega of m. Is this R on the algebra R. Okay, then I will do the following. Okay, sigma takes, then sigma of n, the same sigma n of x, y, and the omega is then the omega of x, omega of y, n large when x and y are algebraic tensor product. So which means that U sigma n, which generate at sigma n equal to sigma n, which and this U sigma n is in the algebraic tensor product M1 tensor n large, of course, much larger than n, and that's the unitary of this. And this sigma n of omega equal to omega. Okay, the translation, the changing this indices carried out by the enautomorphism. That enautomorphism leaving your state invariant. Therefore, this U sigma n belongs to R omega lambda, the centralizer. And once again, this clustering property prevent anything non-scalar commute with U of sigma n. So U sigma n x equal to x U sigma n gives you x is a scalar. So as consequently of R lambda omega prime equal to sigma. Relative commutant is a scalar. Okay, now if you look at the sigma omega, say lambda of t, is the product of the each n Tn. No, not times omega n. Which is given by the 1 lambda it mu it. That's this generates each modulo and the tensoring UN at the modulo of omega lambda. Now, this choice tells you sigma t lambda non-identity for all t, non-periodic. And the spectrum is whole real line. This spectrum of sigma omega lambda, I write sigma is all real line. And this tells you at the same time, which is the same as gamma of sigma lambda, so, which is R. So this one is 3, 1. This is a 3, 1. And since it is approximated by finite dimensional, so it is called approximately finite dimensional factor of type 3, 1. And so consequently, M tilde is to infinity factor. And theta S trace E minus S. Okay, and this is 3, 1 factor of AFD. Now, maybe it's time to, just 1 minute. AFD factors of type 3 is completely determined by the ergodic flow on the center of core. So that means the only 1, 3, 1, 3 lambda factor. 3 lambda factor is only 1, and 3, 1 is only 1, and 3, 0 case as many as ergodic flow. And however, 3, 1 case, that was many people's hand, but 3, 1 is Kohn was unable to prove the uniqueness of this one. That is Hager, another hero in the theory of operator algebras. He proved the uniqueness or very necessary lemma provided by Hager in the 84 summer of 84 he proved. Publication was another year or two. So this is the classification of FD factors. Okay. FD factor 2, 1, 1, 2 infinity, 2, 1, 1 is the Marianne phoneme. 2 infinity Kohn, 3 lambda Kohn, 3, 0 Kohn Krieger, and 3, 1 Kohn Hager. Okay, so this much is, yeah.